Hey there, this is Horner, and this is the Energy Storage and Transfer Model Review Sheet Solutions. So let's go ahead and take a look at these. The very first question that you had deals with three balls that are rolling down three tracks, and they all start at rest, and they all finish at the same point. So the first thing they want us to do was describe the acceleration of each one of the balls as they travel. For letter A, if you think about this is the top of a roller coaster hill and this is the bottom of the roller coaster hill, if you started out at the top of the hill, you wouldn't go very fast, but you would continue picking up speed, and then you would increase your speed at an increasing rate. So here, the acceleration of the ball is low at first, so not much acceleration, and then that acceleration increases. For letter B, the acceleration is constant. Okay, so because we have this straight line here, we will increase speed at the same rate all the way down, similar to what we have for gravity. For the acceleration of C, we'll speed up really quick, and then all of a sudden we'll start to not speed up as quick. So how does that compare to the velocities? So for the velocities, the velocity of the ball increases at an increasing rate on track A. So the velocity will continue to get faster every second, so you'll increase your meters per second every second. On letter B, your velocity will just increase, and then for letter C, it increases really quickly, or it increases at a high rate, and then it increases at a lower rate. And that's the difference between the acceleration, or how you would describe the acceleration, and then how you would describe the velocity. So remember, these first three, these are all about acceleration. And then the next three are all about velocity. Alrighty, let's go ahead and take a look at the next part. So this is probably the hardest part to explain, it's a little harder to understand, but let's try it. So it wants us to rank the time needed for each of the balls to travel from the start to the finish. It's really easy to think that all of these will have the same amount of time on the way down, but that's not true. The fastest one is actually C, followed by B, and then by A. It takes the most time for A to go down. You could think about the potential energy and the kinetic energy and how, because they all start and they all end up at the same spot, that they would be equal. Well, that's true. The potential energy and the kinetic energy for each one is exactly the same. So the speed at the bottom will be the same for each one. However, because the paths are different and because the acceleration is different for each one, they do not hit at the same time. C hits first, then B, then A. The question is why? This graph will help us kind of understand that. We plotted the velocity versus time for each one, and this is the graph you end up with. How did we get it? We actually took the area under the curve, and that represents the change in position. So for C, it would be here. For B, it would be this line. Oops, sorry. It would be the line that we see here. And then for A, you would have a line here. And you'll notice that the change in displacement is almost the same for each one. C, if you look, has a pretty long path compared to B, and A also has a long path. So C and A probably have about the same amount of distance, and B has a shorter distance. However, because C is going really fast at the beginning, it doesn't take as much time for it to get all the way down. So because of its greater initial acceleration, the velocity curve for C will end here or end first. So notice this is time, and it will end first there. For letter B, it ends second. And then finally for letter A, because it doesn't have much initial acceleration, it actually takes the longest amount of time. So the shortest amount of time is C, the next shortest is B, and the longest is A. If you were riding a roller coaster, you could think of it this way. The person riding roller coaster C would get to the bottom first, then B, and then A. Because C takes off really quick, B kind of takes off at a slower rate, and A takes off at the slowest rate. Let's go ahead and take a look at letter H. Now, letter H says rank the instantaneous velocities of the ball at the mid-height line. So at the mid-height line, this is mid-height. Notice that our potential energy due to gravity is here and our kinetic energy is here. Our kinetic energies are going to be the same for each ball. So for C, for B right here, and for A right here, the kinetic energies are the same. Because the kinetic energies are the same and we know they are all 1/2 mv squared, we know that the masses are the same and the halves are the same. Our velocities are the same at the mid-height. But at mid-range, notice that ball A is here, ball B is here, and ball C is already down here. Their velocities are not the same. Their velocities at the mid-range are now different. C is the fastest, followed by B, followed by A. That should help you a little bit with the time also. So let's go back down and make sure we see that if we look at the velocities of the ball at the mid-height range, that's, remember, left to right, we have the same height for each one. And so here is C, here's B, oops, and then there's A. And we'll see that because they all have the same height, we said they all have the same kinetic energy. At the mid-range line, which is this line, now C has the biggest, B is the middle, and A is the slowest. So the last thing they want us to do is rank the instantaneous velocities of the ball at the finish point. And then they want us to explain our reasoning. They all have the same velocity at the bottom. Why is that? It's because they all have the same amount of kinetic energy. Kinetic energy is 1/2 mv squared. We all know that they start with the same potential energy, and because that is mgh, those are equal to 1/2 mv squared. We can get rid of the masses, and we see that gravity really won't matter because they all have the same gravity. They all have the same height. So the velocity is just dependent on how high each one of them are. Because they all start at the same height and they all finish at the same height, they have the same velocity. Okay? So let's review one more time what's happening in each one of these. The time to go from the top to the bottom is going to be C first, then B, then A. At the mid-height, they all have the same speed, and at the bottom, they all have the same speed. But at mid-range, which is this line, A is going to be the slowest, B is a little faster, and C is the fastest. And because of that, they will not hit at the same time. C will hit first, B will hit next, and then finally A. That is really all that you need to know about A through J. For letter K, they say if the start is 1 meter higher than the finish, determine the heights at which A, B, and C will have half their kinetic energy. They all will have half the kinetic energy at the 0.5 meter line. And we know that because if you look at the mid-height, this is the 0.5 meter line, so that's 0.5 meters, and they all have the same kinetic energy. So that is the answer to that one. If we go on down and we take a look at the next one, they want to know where will they have the half of their final velocity. Well, since the kinetic energy is proportional to the velocity squared, the balls have 1/4 of their final kinetic energy when they're moving at 1/2 of their final velocity. So where is it that they have 1/4 of their kinetic energy? So let's go ahead and let's clean up some of what we have here. So we'll get rid of a lot of this. Get rid of that. We'll get rid of this one. There we go. We want to know where do they have 1/4 kinetic energy. Wherever they have 1/4 kinetic energy, that's going to be right here. This is where all of the balls will have 1/2 of the velocity. And it's because that, remember, the velocity at the very bottom is 1/2 mv squared. So we want to find out where we have half the velocity, and that would be 1/4 of the height. Okay, so we'll move back down. Oops, sorry. We'll move back down to where the question is, and because the kinetic energy is proportional to the velocity squared, the balls have 1/4 of their final kinetic energy when they're moving at 1/2 of their velocity. Alrighty? Um, so that is kind of what you'll see. In other words, if we put in, there's one more way to look at it, the kinetic energy is proportional to, and then if we want to know what is 1/2 of the velocity, we know that kinetic energy is velocity squared. So we have to square the 1/2, which gives us 1/4 of the 1/4 of that kinetic energy. And 1/4 of the kinetic energy would be where we have 3/4 of the potential energy due to gravity, and that would be at the 3/4 from the bottom, or 1/4 from the top. Alrighty, let's go ahead and take a look at number 2. Number 2, we have a baseball, 140 grams, it's traveling at 30 meters per second. So let's go ahead and give it this much energy. Why are we giving it that much energy? Because it has motion. Our system is the ball, and it is the earth, okay? And that is what they told us, ball and the earth. And we know that the glove will move backwards 35 centimeters when the ball is caught. So there's got to be some work coming out. Since we can't look at the glove, we know that we just have work on the way out. They want us to find the average force on the glove. All right, so that should be pretty easy to do. Our original energy here is kinetic energy, and then that is going to be equal to the work coming out of the system. So kinetic energy we know is 1/2 mv squared, and that should be equal to the force of the glove times the distance that the glove has to travel in order to stop that ball. So let's go ahead and put some numbers in. That would be 1/2 of 0.14 kilograms. Remember, this grams needs to be in kilograms. And then our velocity is 30 meters per second squared. And that is equal to the force times the distance. Watch out, it is 35 centimeters or 0.35 meters. From here, if you go through, do your math, and you solve, you'll find out that the force is equal to 180 newtons. And that is in the opposite direction of the motion of the ball. So you could also say that the force here is equal to negative 180 newtons in order to stop the ball. For the next problem, this is number 3, we have a spring whose spring constant is 850 newtons per meter. It is compressed 0.4 meters. They want to know what is the maximum speed it can give to a 500 gram ball. So let's think about this in terms of energy. I have a spring, it has energy. So remember, that is US. That US now is going to be made into kinetic energy because it has speed, so that's K. Our US, remember, is 1/2 kx squared, and that's equal to 1/2 mv squared. We're looking for the velocity, so let's go ahead and solve this equation for velocity. Our 1/2s we can get rid of. We know that k here, we know x, we know m, and we're looking for v. So let's go ahead and solve for v. So v squared is going to be equal to k x squared all over m. And if I take the square root of both sides, I'm going to end up with v is equal to the square root of k times x squared all over m. And I'm just going to leave that there. Let's go ahead and plug our numbers in. So our numbers here are, our k value is 850. The compression is 0.4, but we need to square it. And we're going to divide by the mass, 500 grams, which is 0.5 kilograms. So remember, you need to convert this to kilograms. If we do that, we're going to end up with a velocity of 16.5 meters per second, and that's our final velocity. A bullet with a mass of 10 grams is fired from a rifle with a barrel that is 85 centimeters long. They want us to do an energy bar graph of this situation. So for this one, we're going to see that we don't really know anything about how that ball or how that bullet is being propelled. So we need to go ahead and put work into the system. So if we put work into the system, that work will then make that ball or that bullet fire and come out. So we know that that's converted into kinetic energy. So there is our bar graph. If we assume that the force exerted by the expanding gases has a constant 5,500 newtons, what would the speed of that bullet reach? Okay, so let's go through and let's try to figure out what that is. To do that, we need to go ahead and set up our equation. So we know that work is going to go to kinetic energy. Work is FD. We're assuming that it's in the same direction, so we don't need cosine of the angle. And that's equal to kinetic energy, which is 1/2 mv squared. Let's go ahead and solve this for our velocity. And so velocity is going to be equal to the square root of 2 times the force times the distance, all divided by the mass of the bullet. We'll go ahead and move this down a little bit. So I'm just going to switch something here. There we go. We can move that. And we'll go back to our pencil here again. And we're going to do the square root of 2 times, now remember, the force is 5,500. So 5,500. And we need to multiply that by the distance that the bullet is traveling inside of the barrel, and it was 85 centimeters, so 0.85 meters. And I'm going to go ahead and extend this out. And then we need to divide that by the mass of the bullet. And if you remember the mass of the bullet here, it said was 10 grams. So we can go ahead and put that mass of the bullet in, which is 0.01 kilograms. If you do all your math, you should end up with a velocity of the bullet of 140 meters per second. All right, so I made a mistake, and the number here should be 967. Just a calculator error, that's it. Okay, so that should have been pretty easy to do. For number five, we have a 24 kilogram child. That child is on a 5-meter high slide, and that child reaches the speed of 2.8 meters per second in the ground. So they want us to do a bar graph analysis for this. So here's this kid on the slide, and I know these aren't very straight, sorry. And that's what we have. So we have the kid, we have the slide, and we have the earth. Okay, so the kid slides down, and at the very bottom we have a speed of about 2.8 meters per second. The other thing that we're going to have here is thermal energy. So we know that the thermal energy plus the speed should be equal to the potential energy due to gravity that we had at first. So let's go ahead and do that. We know that we have potential energy due to gravity, so that's UG. And then that is going to be made into kinetic energy plus that thermal energy that we had. They want to know how much energy was transferred to thermal. So let's go ahead and put everything else in. We know mgh is our potential energy due to gravity. That's equal to 1/2 of the mass times the velocity squared plus the thermal energy. We already know the mass of the kid here is 24, gravity is 10, and the height is 5. So that's equal to 1/2 of 24. We can't cross off the 24 because we don't have the mass and the thermal energy. And we have a speed of 2.8 meters per second plus that ETH. So if I take 24 times 10 times 5, I will get 1,200 joules. And then if I have 1/2 of 24 times 2.8 squared, I should end up with 94 joules. So I'm going to subtract that from both sides, and then that should be equal to my thermal energy. 1200 minus 94 is going to give me 1100 and about 10 or so joules, and that is equal to the thermal energy, and that is your answer. For number 6, which is the next one, I have a 1,500 kilogram car. That car is traveling at the pretty good speed of about 20 meters per second. They want us to calculate the kinetic energy of the car relative to the road. So pretty easy to do. Kinetic energy we know is equal to 1/2 mv squared. So this is equal to 1/2 of the mass, which is 1,500, times the velocity, which is 20 squared. And we get 300,000 joules of energy, which is kinetic energy. Here they tell us that the braking force is 6,000 newtons. They want to know how far would it travel before it came to a stop. So right off the bat, we have kinetic energy, okay, because that car is initially traveling. And then in the end, the energy that we're going to have left is going to be thermal energy. And that thermal energy is going to be exactly the same amount as the kinetic energy, okay? The thermal energy we could also think of as work going out. So you could actually do either one of those things. So our system here is the car. We know we have the brakes, and we also have the earth. Let's go ahead and go through and let's figure out what is that distance. So we start with kinetic energy and we end up with thermal energy, but that thermal energy is really work. So we can get rid of this here if we want to, and we'll go ahead and put this arrow pointing out, and we're going to say that that is the work due to thermal energy, and there's going to be a little bit of sound there too. So this is 1/2 mv squared is equal to, and then remember work is force times distance. Well, we already calculated this. We said it was about 300,000, and that's equal to the force, which is 6,000, times the distance, which we don't know. And so now we're going to solve for distance, and that distance is 50 meters. They say if you had that same braking force were applied to the car moving at twice the speed, what would be the stopping distance? So they want us to find the stopping distance for the for that speed. Okay, so there's a couple of different ways to do it. One of the ways to do is to do all the calculations, but I don't want to do that. I know that kinetic energy is proportional to the velocity, but the velocity squared. So how much kinetic energy would it have if I have twice the speed? So if I multiply the speed by 2, that means that I'm going to square both the 2 and the velocity. So that means my kinetic energy now is proportional to 4 times that velocity squared, or I have 4 times the kinetic energy. Because I have 4 times the kinetic energy, if I know that 4 times the kinetic energy, that will give me 4 times the work. And I know that work is 4 times the force times the distance. And if the same average braking force, so we're going to keep the braking force the same, that means the only thing I can multiply by 4 is the distance. So the distance will be 4 times further. And that's why you have to be really careful when you're driving, because the faster you go, it takes you 4 times further every time you double your speed. All right, let's go ahead and take a look at the very last part. We have 2 bombs are dropped from a target of 3,000 meters. So we have a height here, and we know that height is about 3,000 meters. We know that at the top, both bombs are up here, so we have bomb A and we have bomb B, and we know bomb A has 3 times the mass of bomb B, so 3m, and this one is just m. So we need to find the value of the ratio of the potential energy due to gravity to the potential energy due to gravity of A. So the potential energy due to gravity of B is mass of B times gravity times the height of B divided by the mass of A times gravity times the height of A. And because the two heights are the same, we know that we can just get rid of those two heights. Gravity is the same, so we can ignore those. And we know that the mass of B is going to be 1, and we know the mass of A is 3. So the value of the ratio of the energy is 1/3. So it is 1/3 the potential energy. So A has 3 times the potential energy of B, or B has 1/3 the energy of bomb A. So just before the two hit the ground, or at the moment of impact where they have maximum speed, they want us to determine the ratio of the two velocities. Okay? So in order to do that, what we're going to do is we need to... All right, so we had a little glitch there, but we're back. And so when we look at this, we see that we've got the two balls, and we know that this one is the larger of the two. And remember, we said that the larger bomb is A. So actually, what we'll do is let's move bomb B over on the other side. So here's bomb B. Here's bomb A. It is much bigger. But if you remember, when things fall, it is due to the acceleration that they fall. So the acceleration is the same for both. So they will both hit the ground at the same time. Even though they hit the ground at the same time, we know that the kinetic energy for this one is bigger than the kinetic energy for this one. But it's not because of speed, it's because of mass. This one has a much bigger mass than this one does. So the ratio of VB over VA is equal to 1. They both have the same speed at the bottom, but they don't have the same kinetic energy. They want to know, how does the acceleration of the bombs compare? It is exactly the same. Remember, gravity is going to be equal to 10 meters per second squared, so it is exactly the same. The confusing part about letter B is you think about kinetic energy when you really just need to think about speed, and that's the difference. For the very last one, we have a force probe. So I'm going to make this a little bit smaller. It is used to stretch a spring by 20 centimeters. So here's our 20-meter stretch. The graph of a force versus the function of distance is shown, and kind of tells us what's happening. It says determine the spring constant for this spring. So to do that, we're going to pick 2 points. We're actually going to use the 300 up at the top, so that's on the line, and we're going to use the 0 because that's also on the line. That makes it a lot easier. So our spring constant, remember, K, is equal to the force divided by the change of position or the stretch. The force here is 300 newtons, and we're going to divide that by 0.2 meters. Why 0.2 meters? This is in centimeters, so we need to divide it by 0.2 meters. And if I take that 300 and divide it by 0.2, I should end up with, 300 divided by 0.2 is 1,500 newtons per meter. So be careful. It's tempting to say that it's 600, and it is not. It is divided by 0.2, and so it is 1,500 Newton meters. It says determine the energy in the spring, US, using the area method. So if we use the area method, remember the energy in the spring is equal to, or the work of the spring is equal to the change in energy, and so that would be the stretch of the spring times the force. So energy or change in energy is equal to work, and that is equal to the force times the distance. And because our area here is a triangle, we know that the energy, or the change in energy, is equal to 1/2 of the force, which is 300, times the distance as the spring is stretched, which is 0.2 meters. So you have to remember that 0.2. So that would be 150 times 0.2, and we get 30. So the work, or the change in energy here, is equal to 30 joules. Determine the spring energy using the potential energy spring formula in the AP Physics 1 equation sheet. So remember, the work done by a spring is equal to 1/2 of the K value times the stretch squared. So this is going to be equal to 1/2 times, remember we found it earlier, 1500, and then our stretch was 0.2, and we need to square it. And so now we've got 1500 divided by 2, and then we're going to take that times 0.2 squared, and we end up with exactly the same thing, which is 30 joules. So we found it using the area, and then we went back and we found the energy in the spring using our good friend, the spring energy equation. And that is almost the end. We're on number 9. Number 9 says a physics teacher rents a really nice sports car that has 450 horsepower, so 450 HP. How much time would it take to use 124 million joules of energy in a gallon of unleaded fuel? So I know I have 124 million. So I could write it out joules, or I could put 124 times 10 to the 6th joules, or I could do 1.24 times 10 to the 8th joules. So any of those three would work. You can do it any way you want to. We need to go from the 124 million joules. We also need to convert the horsepower into watts. So let's go ahead and do the horsepower into watts first. So 450 horsepower, I know that in 1 horsepower I have 746 watts. So I'm going to take 450 and I'm going to multiply that times 746, and at that point I get 335,700 700 watts of power. What is that? Remember, that's also equal to a joule per second. So here we're going to say we have 335,700 joules of energy every second. Okay? So now they want us to figure out how much time it would take to use that 124 million joules using this car. So let's go ahead and try to find that time. We know that power is equal to work divided by the time. So our time would be equal to our work divided by our power. The amount of work that we have is 124 million joules. Now it says energy, but that is doing work for us. So we're going to put 1.24, so it's 1.24 times 10 to the 8th joules, and we're going to divide that by the power, which we said was 335,700 joules per second, and this is joules. So when I divide the two, the joules cross off and the seconds go on top. So we're going to do the math now. 1.24 times 10 to the 8th divided by that 335,700. And we end up with 369 seconds, or 369.4 seconds, so 369 seconds. If we want to know how many minutes that would be, 369 seconds divided by 60 would give us 6 minutes and 6.15 minutes. So I could drive for about that long. Alrighty, let's go ahead and take a look at that, and that means I'm going using the entire 450 horsepower, so I must be really moving. Very last question. It says, how many kilowatt hours of energy does a 4.2 watt LED bulb use if it's left on continuously for 24.125 hours? So I'm going to start with 4.2 watts, and if I want kilowatt hours of energy, I need to convert the watts to kilowatts. So I have 1,000 watts in 1 kilowatt, and if I divide the two, 4.2 divided by 1,000, I'm going to move that decimal over, and I'm going to get 0.0042 kilowatts. It's going to run for 24.125 hours. So remember, the energy here is going to be kilowatts times hours. So I want kilowatts times hours, so 0.0042 kilowatts, and I'm going to multiply that times the number of hours, which is 24.125 hours. And let's see what we get. So 0.0042 times 24.125, and that is 0.101 kilowatt hours. And that is the end of the review.